think about games in a mathematical way. Okay, so some terminology for games. So the topic here will be what is called parity games. Okay. Parity games. But so this parity games in this here it's maybe not that thing which we may be thinking. It is that the two players will be playing. That's the kind of game this will be, and these games will go on forever. Okay, but in the beginning, let me just describe some terminology, which, as I said, will help you to think about games from a mathematical perspective. Which facts that you think are true, you can prove. Some general, algorithmic things that people use, you'll get used to through this kind of abstract example. Okay, so maybe I'll erase this and I will call this games played on graphs. Okay, games played on graphs, and this you can then use. All kinds of games can be modeled as games on graphs. So games played on graphs. Okay, so what is the setup? The setup here would be that you have G is a graph. Okay, G is a graph. So I will not define. I think you people know what a graph is.
Yeah.
Yes. Okay. That means I do not want a very precise definition. That is not needed. If you know what it is, then that is fine. Okay. G is a graph, and G is a graph, and just a minute. And now the vertices. Now let's call this. Divide this into two. So the set of vertices we are dividing into two parts. Okay, this is usually not done, but okay, so let me then not do it like that. See, VE. So these are vertices and edges, but then we will give a further subsets. V1 and V2 are again subsets of V. Okay, V1 and V2 are again subsets of V, and these are going to be maybe again let me change the notation, because we will have, for some reason we will use 0 and 1. That's better for some reason, and we want this. Okay, we want that the disjoint union, this adds up to V. Okay, so basically the vertices of the graph are being partitioned into two parts. Okay, one set of vertices we are calling V0, another set of vertices we are calling V1. Okay, and can anybody guess what this V0 is supposed to, what it's supposed to convey? Right.
So I don't know where V0 came. Like we have V1 and V2.
Yeah, so I've just replaced that by V0. Yeah, so I forgot to replace
Okay.
it here. Just
So
replace.
is it
Maybe
like
moves where player one has played, and the moves like V not could be the moves where player one has played on the vertices, and V
Yes,
one
exactly.
can be there too.
Exactly. So this Vi would be vertices of player I. Okay. So as I said, this game is going to be infinite. So it's going to be something like this. Okay, like when the game is at vertex I, then if that or the game is at vertex K, and if that vertex K belongs to player 0, or if it belongs to V0, then player 0 can make a move, and what that is we will describe. And otherwise, if it's a vertex for V1, then in V1, then player 1 will make a move. Okay, so and the players will be called 0 and 1. Okay, so then we will now what is a game? The game I've already described, but then the game there will be a starting vertex. We will just call it like that, V0. So V0 would be like a starting. This is obviously different from that V0. Okay. This is the starting vertex. Okay, and then as I said that at the ith stage, Okay, suppose if the starting vertex belongs this small v naught, if this belongs to capital V naught, then player 0 will make a move, and that means he will go to a different he will choose a different vertex. That vertex could be any vertex in the graph. Okay, he could choose a vertex that again belongs to capital V naught, and then again player 0 will make the move. Okay, or it will be will be going like that. All right. So you could also imagine that starting vertex, you could also imagine here that a token is placed. Token is placed at V naught, and the token keeps moving according to what I have said. Okay. Now, so this is what I've discussed. This is where the difference comes, where you people have to understand. This is something that everybody understands. Okay, but we want to make it slightly mathematical. Okay, so the game is infinite and so on I've described, but now we want to view the game as a sequence. Okay, so I'll just write this: every game is an infinite sequence, right? Infinite sequence. And so like what? So it's like we start with V naught, and then you don't know where it's V naught, V2. Infinite sequence of vertices. So this is a member. This is basically a member in, where is it? Just if you want to do this like mathematically, it is in that V, big V, V cross V cross V infinitely many times. Okay. All this may look useless, but thinking about games mathematically is like the foundation which we are trying to sort of build. Okay. So that is what a game is. So now a game is a sequence. Okay. You will see why we are doing like this. It's very, very useful, because even to do the reasoning, we may have to go from one sequence to another sequence, and we may have to look at the class of sequences. So it's good to see it as a mathematical structure rather than saying, oh, what if the game was played like that? What if it is like that? It becomes much more systematic, and the tools of mathematics become available to you. Anyways, so the game is the sequence. Now, how do you basically what should I say? Yeah, we can just do that. Right. Okay. So now outcome of a game. Yeah, let us describe this outcome of a game. So can anybody like try to see how should I define outcome?
I don't know, because you are seeing an infinite game.
Yes. Right.
But I don't know how to define the outcome then.
Yes, and you are correct. In fact, when I was thinking of outcome, the first thing I got stuck as, yeah, it's an infinite game, so what should the outcome be? Correct. But then I know because I've read it. So yeah, that is why I was slightly also confused. So yeah, outcome of a game will be defined very, very abstractly. So what is an outcome? Outcome is, well, you would say, but there is no rule or whatever, but at the end of the day, the outcome is an association that associates every game to a number. I'm not writing that, but you understand, right? It associates every game. So given a game, which means given a sequence, it associates it to a number, right? So an outcome of a game or outcome, I'll just say a game maybe, but the outcome. So outcome will be defined as a function, as an association, right, from a game to a number. So it will be defined as a function. But let me use a terminology which is standard, because that is very, very important in this. Because I remember when I was trying to read this kind of stuff in BSc times, I could not read the book because the terminology was so common. Even if you try to read it now, it will be difficult, but soon it won't be. But it's important to get the terminology straight. So this is called a payoff function, and I don't need to motivate the terms. You guys understand what this kind of trying to say. So here this is a function from v cross v infinitely many times, and that infinitely many times we will write like this. This you may or may not use. You can just use Cartesian product infinitely. This is just a notation. Okay, just a symbol. But let me also use a symbol for the function. The function symbol, we are not going to write f, we are going to write pi. Okay. Usually you write f, you can write f, but I'm just going to write it as pi. Okay. So this pi is actually the function. This is just the colon for English, but this is the colon for mathematics. And this is a function from here to r. You could also take infinite, I suppose. You could also allow you the number infinite, but fine. I mean, it doesn't matter. Okay. So now
So
is
in
the
the last is no one winning, or is no one? It's not like a win or lose game. Just like it, the game yields a number. Is it like that?
That's a very good question. Yeah, the game certainly yields a number. Okay. And whether it's a win or lose game, that will depend on what the range is of this function, right? Yeah.
Okay. Okay.
And obviously we have not defined win or lose so far, but that answers your question. And whether such a and then even if such a number is outcomed, whether it makes sense to say that the game is sort of, you know, has a, like, I mean, even if there is no win or lose, there is any sense of win or lose or not for the game, any sensible sense of win or lose or not for the game, that is actually a big question. That is not at all clear from just the function. Okay.
Okay.
So let's see, Aryan, can you tell me what should be the range of this function for this to be a win or lose game? Whatever you think about what a win or lose game should mean.
So range of the payoff function.
Yes, meaning that you understand, like, if what should be the possibilities of the outcome, so that we can call this a win or lose game.
Okay. So I think it depends on the game, but if I had to guess, I would say n, like natural numbers.
Natural numbers. Okay, so for you, what is a
Or
win or
ray.
lose?
Okay, wait, no. I think it should be just one number, like some set containing one number or
Right.
something like that.
Yes, correct. Yeah. So it's not one number, but yeah, I understand what you mean. It's two numbers, 0 or 1.
Two. Okay.
0
Yeah,
or
yeah.
1. You can,
Okay.
yeah, you can feel it, right? All right.
Yes, sir.
Okay. So, Nagesh, have you studied games ever during your studies, undergrad and so on? Have you studied games?
Yeah. We built a chess engine once, so
Okay, right. So then
there.
you can relate to this terminology with that. You try to do that. Okay, from maybe just on the go, you can try to do that, right? It will be, then you'll already have examples with you.
They will have three results, right? Like win, lose, or draw
Right.
for a chess game.
Yeah. There is, there is three there, I suppose. Probably there are generalizations. Yeah. Okay. Right. Yes. So what should I do now? I will look at this payoff function, and I will not call it just a win-lose game. I will call it a qualitative game. Okay. Qualitative game is sort of, because see, I mean, even if the outcome, so far we don't have any examples, that is one of the problems. But see, even if the outcome is, like, it could also be a number, right? That, like, you're moving and then some sort of a token counter is increasing, right? How many steps are taken to reach a certain vertex. So it could still, win or lose game can still have, in a way, but those are just, we have not even defined, so it's not very clear to talk about it. But I will define what is called a qualitative game, and this is basically the win or lose game you're talking about. Okay. And this is when this is basically when range pi is 0 or 1, or maybe it is better to say contained in 0, because some range means you have to, you understand. Okay, when range pi is contained is 0 or 1, so basically the outcome would either be 0 or it would be 1, means basically that we are trying to do something, right? It could be something like the game starts at v0 and there is a target vertex v final, and the goal of let's say player 1, keeping with the example I have in mind, which later will actually solve the algorithm for, will develop the strategy for. Let's say there is a vertex v final, and the goal of the player 1 is to reach that vertex somehow, right? whenever he gets his chance, he would try to reach, he would make sure that he develops a strategy to reach that vertex, and player 0 would try to avoid that. In that case, you see, in that case, in the infinite sequence, the output will either be 0 or 1. If you have reached, if that sequence contains that vertex, final vertex which you want to reach, then it means player 1 has won, right? And then then the will return 1 for those sequences, otherwise we'll return 0. So that's the what I'm talking about. Those are like the qualitative games, and in fact those are the games we will talk about. The other ones, quantitative ones, I suppose, yeah, will need some more linear programming and so on, which we will not do right in this. Okay, so do it later. Okay, so this is the situation, and now basically the outcomes, right? So these are the outcomes of a game, and now here is a question. Okay, can you define what is winning outcome? For now we only focus on qualitative games. Okay, only focus on qualitative games. You have a example in mind. Okay, now can you describe what should be winning outcome? Can you describe it mathematically? Then we'll move on to what is strategy. Mathematically, what is a strategy?
So there are only two outcomes possible, right? 0 and
Yes,
1. Like
yes,
over here, the game we are talking
right.
about.
Yes. So winning
I think
outcome,
it should be 1.
yeah, and actually the question is not well defined. So, but yeah, it's winning outcome. Let's say winning outcome for player 1 is when the outcome is 1, right? When the outcome of the game is 1, then that is winning for player 1. Okay. Otherwise, it is losing. So yeah, so this here in this case there will be no draw, right? And so that would be pi inverse of 1. Pi inverse of the set 1, but anyways, pi inverse, you understand, right? So all those things which actually map to 1, these are actually important, because later on when you have these things, okay, these are inverse of a function and so on, inverse image, because inverse images behave very nicely with intersection and so on. When you actually want to prove things, that something happens or something we'll talk about, then it actually becomes very, very convenient. Okay, so we have defined winning outcome. Now we need to define what is a strategy. Okay, so let's erase a few things. Yeah, strategy. So we are just defining things and quickly getting comfortable with them. Okay, that is one of the other key things in when you're doing any kind of mathematics, especially when you have to answer questions. Just new things are defined, you get comfortable with them, and yeah. So now tell me, how should we how should we define a strategy? How should be a strategy?
So, like an algorithm that a player can follow to get to the winning outcome.
Okay, that is fine. No, but strategy is not always winning, right? It doesn't always.
No.
Yeah.
Okay, to maximize. Okay, maybe to maximize your chances of winning. Yeah, maybe.
No, but that would be optimal strategy. Yeah, but a
Okay.
strategy in general, like just what is a strategy as a function? Yeah, so I suppose that would be difficult to just think immediately. So the strategy would be a function. So let's see, what is a strategy? A strategy is something like this, right? You you are at a position in the game where, let's say, the token is at the ith vertex. Okay, and you'll make a move from there, right? So certainly um, so let me just check what is the notation of making a move, because
So is it like
that
a permutation of uh V or V naught or V1? Like because like a set of moves, a sequence of
yes,
moves.
well, that is correct. It is a permutation, but yeah, a strategy. No, but see, what we want to do is the following, right? We want to say that there is a strategy which is yeah, I mean, let me just say it like this. So basically, in a strategy, we have to first see where we are. Okay, so let us say that you are at the Vth vertex. Okay, V in V. Okay. And now you look at what are all the moves that have been played so far. Right. What are the moves that have been played so far in the game? Okay. So let us say that is, let's say that is small v1, small v2 till small vk. So far, okay. And also then you are at v. Right. And then looking at this situation, you make a move, which means that you take this string, because the move that you make will depend not only where you are. In most cases, it will depend only on that. But in general, it is not only depending on where you are at the moment, but what is the situation of the game completely from where you are coming from. Right? So basically, looking at this whole string, right, and the vertex where you are. So the game started at v0, then it went to v1, it went to v2. So it will depend on, like, these are small vi. So depending on this vi belonging to vertex for player 1 or player 0, they'll make their moves. But then it goes to vk and then it goes to v. Now the whole journey, depending on that, we will have to go to some vertex w, right, where w is also in capital V. Okay, and this we will say as a function, this we will call new. This will be our strategy new, but obviously there will be some conditions on this function, right? What are the conditions? Well, the conditions would be the following. So if new, let's say that new of this thing is equal to w, okay, this implies that v comma w yeah, so tell me, what should be the conditions on this function, right? So, well, it will clearly depend on where the small v belongs, whether it belongs to v1 or v0, right? So if the small v belongs to v0, then that implies, what does that imply? I mean, actually, it won't depend on that, but yeah, it implies that v comma w is an edge, but it has to be an edge to begin with, right? Is an edge, right? It has to be an edge. And well, actually, now you realize that actually that it doesn't depend on v, that which one it belongs to, but it depends on the fact, I mean, certainly it has to be an edge in the graph. You can't just take any v2. So that in that sense, it's not an arbitrary permutation, right? So the whole point is that the v comma w has to be an edge in the graph. Yeah, you can, is that correct?
So like you can't like jump around in the graph. Like you
Yeah,
can only move on the edges.
yes, I mean, that's why the
Is
structure of the
that what?
graph is interesting. That's why, yeah.
Right. Yeah.
Otherwise, the graph, otherwise it's just a complete graph.
Okay.
Then we say it's a complete graph if you can just move around.
Yes.
Yeah.
Right.
And
Yes, sir.
right. So, right. And I mean, um, in fact, I mean, as you can understand, right, I have probably made a little mistake. Like the strategy should be two. There should be one strategy for player 0, another strategy for player 1, right? But you understand this is the situation. I mean, it is a bit more complicated than this, but that I find is not needed in our, yeah. So that we will not discuss. It's something like we take the language on V, something called a language on V, which is just a collection of all strings, and the function is from there. But that's not needed. You understand what this is, okay? In fact, what we will be more interested in is what is called a positional strategy. Okay, so let's see. So this strategy, as you can understand, depends on the entire game that was played up till that point. But now let me write this thing, positional, and you try to define it, it's very important that you try to define it once. And that's, I think, I try to do that when I study. Yeah. Or if I have time in the class. Usually the class goes very fast in college, but yeah, we try to, yeah. Positional strategy. Now we should be precise because there are two strategies, of course, for player 0. Now tell me, what do you think positional strategy means? It's sort of what I've been highlighting, I think. But yeah.
Depending on where you start.
Right. Depending on where you start. And but it not just where you. What do you mean by where you start?
Like on the first vertex.
Very first vertex. Okay, no, cool, but no, there should be something more, right? I mean, positional strategy. So it should depend on where you are also, right? Which vertex you are, which vertex the game is at, right? The strategy is defined for, yeah.
You have to choose an edge, yeah, which will take you to the winning vertex.
Right. So we have to choose an edge, but what will that choice depend on? So you are saying that position strategy for player 0 would be that given V in V naught, you associate V to some W. But anything more?
The choice of edge will be dependent on which which vertex you're on.
Yes, which means it's a function. Like it's a function, right? So given that vertex V, you choose a vertex F. So it's a function. So it's a function. Let's call this also mu. Right? Anything more? No, nothing more. And that is why it's called a positional strategy. Do you see the difference between this and this? Here it is not just based on which vertex you are at, but the entire string of the game so far. Right? The sequence of vertices that have been visited so far in the game, and at every stage it will be finite. It's an infinite thing, but at every stage it is finite, right? Just like natural numbers. But positional strategy is just this. So it's a function. It's a function from just V naught for position strategy for player 0, just a function from V naught to V. V naught means the capital V naught, right? To V. And obviously
So
the
it's like
condition.
we are defining the move which we want to play, the next move, just a next move.
Yes,
Like
just a next
the
move.
function.
And yeah, and it doesn't depend on anything but just where you are at that point. So like what you were saying about starting, I suppose this is what you mean by starting, what you should mean by starting, right? Like where you are at
Yeah.
that point. Only depending on starting doesn't make any sense. Yes.
So if we have suppose we have a game where it doesn't it never depends on like the previous moves. It only depends on like the current state of the game.
Hmm.
Then the strategy function will be equal to the positional strategy function, right? For a certain player.
So no, but what do you mean by the game doesn't depend on the previous vertices? Game, that is.
Like I suppose if you have a I don't know like how to define it properly, but like what is the condition for the strategy function to be equal to the positional strategy function? Or like can it be equal ever?
Can it be equal? Well, as a function, it cannot be equal, right?
Okay.
Because they have
Yeah.
different domains, right? But I understand what you're saying. You mean that you mean that, yeah. So you are saying the following, I suppose, that if suppose you have the strategy, and in the strategy this string goes to W, then any other string, any length actually, any other length also, as long
Yeah,
as it
yeah,
ends in
yeah,
V, it goes to W.
yeah. Something
Yeah.
like that. Yeah.
Yes, and in fact,
I
this
mean,
is
as
how.
functions, they can't be equal
Yes,
because
but it is sort
yeah,
of
but
invariant, right? I mean, it doesn't depend
right.
on this initial string, right? Yeah. So this initial
Yeah,
string V is equal to any initial string W, right?
yeah.
Yes. And in fact, this is how one should define positional strategy as a special case of strategy, as a special class of strategy functions, which this happens, and this is basically the small 1 mark question, right? The strategy is equal to positional strategy if this happens. like what collection of strategies can be recognized as positional strategy. Okay, because that's how mathematics should be, right? When you're defining strategy, and then when you define positional strategy, it should be some special classes of strategies. I have just defined it as a different function, which is the correct interpretation in the end. In the end, you can think about it like this, just a function from V to W. But in the beginning, it is not, and that's better to, yeah. Because what may happen is that you want to prove something about a game in which a positional strategy works, but then you're doing some sort of induction or you're reducing the number of vertices, then you may need to just go back to strategy. Okay, but if I've defined positional strategy as something which is mathematically very different from strategy, then it will be difficult to do the mathematics there, right? Yeah. But if you define it as a special case, then you're in the same structure and you can do things. So anyways, this is so far we are just defining these things, but you see, just these definitions also have some intricacy here. Yep. Okay, so now what should we define next? Now we'll define I don't know what to call it, value of a game or something. I'll have to look at the book what they call it. I know the definition, I know what the definition is, but I don't know the term. Let's see. All right, so maybe this also we can erase. And there is some deep mathematics also lying here, some deep analysis and measure theory, like interesting stuff that is used to prove things about these, but we will not go in that. But yeah. So so we have a game, we have a game graph, we have a payoff function, and yeah, so they don't actually call it anything. Okay. But yeah, in the end, we want to look at the following. So it's something like this. If you can think of it like this, that if you look at the initial payoff function pi, right? It's called payoff for a certain reason, right? This thing is called payoff for a certain reason. So suppose that you play a game, okay, and this obviously it actually goes on. Yeah, this thing. Then this is a real number, right? Let's say that it is 10. Okay, now this means, the way we define it is that this means that if the answer is 10, then player 0 has to pay 10 units to player 1, right? Okay, and so this basically just what we're just trying to say is that the goal of player 1 is to maximize the outcome, is to choose a strategy so that the outcome maximizes, and the choice for player and the goal of player 0 is to minimize the outcome. Everybody understands that, right? I'm just saying simple stuff. But then how do you see it as a function? How do you see that as a mathematical quantity? So this will basically be the following. So yeah, it will so let's call this outcome. Okay, outcome. Right, so suppose the game starts from V0. Okay, the game starts from, yeah, but you have to just be careful. That's the only thing, defining things here. The game starts with V0, and let's say that Chi is a strategy. This is a strategy for player 0, and this is strategy for player 1. Okay, yeah, I suppose the time is almost up. So how about we meet right after this meeting ends? So again, let's just take a break for 5 minutes and then we will meet. Okay, is that okay? Right, yeah, just try to take a break
Yes,
for
sir.
a few minutes and then we will meet. Yeah,
Yes.
all right.